Some integrals are best solved with a t-formula substitution. Before we jump into the t-formulas and refreshing how they come about, let's identify what type of integrals we should use these. So it's for integrations of the form 1 on some cos x value plus some sin x value, or 1 over a cos x value plus a constant, or the same but for sine of x. So if we see any integrals of this form, it's best to use the t-formulas. So the t-formulas, remember, are these guys. We start with t being equal to tan of x on 2, so that's our substitution, and then we can derive from that sin x, cos x, and tan x, these expressions. How do we get them though? Well, let's start from scratch. If t is equal to tan of x on 2, then we can come up with a pretty simple right-angled triangle, where x on 2 is our angle in here. In order to satisfy that tan of this angle is equal to t, well, tan in a right-angled triangle is opposite over adjacent. We want that ratio to be t, so let's call our opposite side t and our adjacent side 1, and that way we see that this condition is met. What's the hypotenuse going to be? Well, applying Pythagoras' theorem, we get root 1 plus t squared. This then allows us to come up with expressions for sine of x on 2 and cos of x on 2. Sine is opposite over hypotenuse, so we get sine of x on 2 is equal to t on root 1 plus t squared. And for cos, well, we're dealing with the adjacent side over the hypotenuse. However, we are after expressions for sine of x, not sine of x on 2, and for cos of x, not cos of x on 2. What we can do is apply our double angle rules. So let's start with the double angle rule for sine. Sine of 2a is equal to 2 sine a cos a. So let's replace a with this angle x on 2. We get sine of 2 lots of x on 2 on the left, and so that just simplifies to sine of x. And then what about the right hand side? Well, we have expressions for these two, so let's substitute those in. We can then simplify by multiplying the numerators and multiplying the denominators. So what are we going to get? Well, on the numerators, 2 times t times 1 will give us 2t, and on the denominators, we can see that the square root signs will just cancel out. And so we have our expression for sine of x. Now let's look at finding our expression for cos of x, and we're going to use the same idea as we did for sine. Let's look at the double angle rule. So cos 2a is equal to cos squared a minus sine squared a. And once again, let's replace a with x on 2. When we do this, we see on the left-hand side that cos of 2 of x on 2, well, that simplifies nicely to cos x. And what about the right-hand side? Well, we have cos of x on 2 all squared, and we know that cos of x on 2 is 1 over root 1 plus t squared, so we can square that. And then we also know what sine of x on 2 is. It's t over root 1 plus t squared, and so we're going to square all of that. focusing on the first one, when we square 1, we get 1, and the square root of 1 plus t squared, when we square that, we just get 1 plus t squared. And in the same way, when we look at our second fraction, we get t squared on the top and 1 plus t squared on the bottom. Now both of these fractions have the same denominator, so it's very easy to combine them. And so, after this manipulation, we now have our expression for cos of x. One more to go, and that is tan of x. This one's a little bit easier, no need for double angles. Because we know that tan x is sine x on cos x, we can simply sub in the expressions that we've already developed. So sine x is 2t over 1 plus t squared, and cos x is 1 minus t squared over 1 plus t squared. So there's sine x divided by cos x. Now when we have one fraction divided by another, we can use our times and flip. And we notice that the 1 plus t squared here cancels with this 1 plus t squared, leaving us with 2t over 1 minus t squared. And this is our final expression for tan of x. Before we do some integrals, do some actual examples, there's one more thing that we need to cover. When we are making a substitution, in this case it is t equals tan of x on 2, we go from our integral being with respect to x to being with respect to t. So we need to derive this expression and find a link between dt and dx. So let's do that now. The derivative of tan is sec squared, but we need to account for the x on 2. So a half is going to come out the front. Sec squared and tan squared are related to each other. There's a link between them. Let's remember, if we start with the identity sine squared plus cos squared equals 1, we can adjust this. So let's divide through each of these terms by cos squared. That gives us tan squared plus 1 is equal to sec squared. And so if we write this in the following way, that means back over here we can replace sec squared with 1 plus tan squared. And so we have the following. But remember, tan of x on 2, well, that's just t. So tan squared of x on 2 is just t squared. All we have to do now is double both sides, and also we will move the dx over to the right hand side, and to get dx by itself finally, let's just divide through by this 1 plus t squared. And so this is how we can replace dx with dt. And so now it's time to do our first example. Use the substitution t equals tan theta on 2 to show that the integral between pi on 2 and 2 pi on 3 of 1 on sine theta to theta is equal to half log base e of 3. So, given this substitution, t is equal to tan of theta on 2, we know from the work we just did that sine of theta, right, that's what we want to use for this question, sine of theta, that is 2t over 1 plus t squared. And we also know the link between d theta and dt. D theta is equal to 2 over 1 plus t squared dt. Now, because this is a definite integral, we also need to adjust our lower bound and upper bound. When theta is equal to pi on 2, t is going to be tan of pi on 2 divided by 2. So that's tan of pi on 4. And what is tan of pi on 4? Well, that's just 1. We also need to adjust 2 pi on 3. So when theta is equal to 2 pi on 3, t is equal to tan of 2 pi on 3 on 2. So that's just pi on 3. And what is tan of pi on 3? Root 3. So this means we can express our original integral as the integral from 1 to root 3 of, well, it was 1 on sine theta. So 1 over sine theta, if we're going to express sine theta as this fraction, 1 over that means we are going to flip that fraction. So 1 over sine theta becomes 1 plus t squared over 2t, and then d theta is getting replaced with 2 over 1 plus t squared dt. Now look at the amount of things that cancel out. This is quite nice. We see that the 1 plus t squared will cancel out, and also the 2, leaving us with 1 on t. The integral of 1 on t is the natural log of the absolute value of t. And so all we need to do now is evaluate this. Because root 3 and 1 are both positive, we can ditch the absolute value signs now. And what is log of 1? Log any base of 1 is just 0. So this is simply log base e of root 3. However, remember we were asked to show that our integral is equal to this. So we're close, but not quite. Well, just using a few of our log laws will help us out. Root 3 can be expressed as 3 to the power of a half. And when we have a logarithm and there is a power in here, we can take that power and put it out the front. And there we have it. Now finally, we are going to talk about integrals that lead to solutions involving inverse trig functions. So the first integral that we will look at is the integral of 1 on the square root of 1 minus x squared. This is the inverse sine function. If we make a little bit of an adjustment and rather than 1 we have some a squared value, then the effect that has is that our integral solution is inverse sine of x on a. Finally, if we're not just dealing with x, but rather some function of x, and we apply the chain rule, then what we get is inverse sine of the function of x on A. And this last one here is what you'll find on your reference sheet. The integral that gives us inverse cos of x is actually just the negative version of this. So negative 1 over the square root of 1 minus x squared gives inverse cos of x. And likewise for these if we extend them. However, we don't actually find this formula on our reference sheet. Rather, we find the differential version of it. That is, if y equals inverse cos of f of x, then the derivative equals minus f dash x over the square root of a squared minus fx all squared. So we can use this if we need. However, if we do see an integral of this form, simply dragging the negative out the front then allows us to use the inverse sign, like we saw before. Okay, let's go on to inverse tan of x. If we have an integral of this form, then our solution is inverse tan of x plus our constant. Once again, modifying it slightly so that we have an integral that looks like this. This time, our solution has a 1 on a out the front, and then our inverse tan of x on a. Finally, if we have some other function of x, so our integral looks something like this, then our solution is 1 on a inverse tan of our function of x on a. And it is this final expression that is on our reference sheet. But why have I been talking about these in the videos for integration by substitution? Well, sometimes we can evaluate these integrals not just by using the reference sheet and what we know about inverse trig functions, but also through appropriate substitutions. So we're going to do one last example, and we will do it via two methods. First, we will look at using what we've just talked about, and second, we'll do it with a substitution. Evaluate the integral between 0 and 2 of 2 over the square root of 16 minus x squared. So the first way we will do it is using the reference sheet. Observing this integral, we notice that we have a square root on the denominator, and we also have some value minus x squared. This should lead us to consider the following integral on our reference sheet. Comparing the two, we notice that we are just dealing with x rather than some function of x, which is good. And our a value is 4, because 4 squared is 16. This 2, we might just bring that out the front of our integral because that's just a constant. So let's take our original integral and put it into this form as much as possible so that we can easily transfer it into this. So the 2 is out the front. We have just a 1 on the top now, and we will write 16 as 4 squared. Now we can see that we get 2 inverse sine of x over a, which is 4 in our case. And so now we can go about evaluating this integral. First of all, when we substitute in 2, 2 over 4 simplifies to a half. And when we substitute in 0, we just get 0. Now I encourage you to actually visualize the inverse sine graph when you need to evaluate expressions like this. Remember, it has a shape, a little something like this, but because it's an inverse function, along the x-axis we have 1 and minus 1, and along the y-axis is where we have our pi units. So this is pi on 2, and this is negative pi on 2. At the same time, you can always ask yourself, instead of what's inverse sine of a half, you could say sine of what gives me a half. And we know that sine of pi on 6 gives us a half. And that sine of 0 gives us 0. Once we've done that, we just have 2 lots of pi on 6. And that simplifies to pi on 3, which is our answer. Let's try this question now using the second method of substitution. In this case, we are given the substitution x equals 4 sine theta. But what if we aren't given the substitution? Well, in our case, because our integral we know leads us to an inverse sine solution, that is why having sine theta, a of sine theta, is appropriate. And in fact, we could use 4 cos theta as well. If our integral is one that leads us to an inverse tan solution, then using the substitution x equals a tan theta would be appropriate. We can also use the substitution x equals a sec theta for integrals that look like this. But in most cases, if you are told to solve one of these integrals using substitution, then it will be given to you. Alright, so let's go ahead and complete this integral. Since we know x equals 4 sine theta, we can say that the derivative of x with respect to theta is 4 cos theta, meaning we can replace dx with 4 cos theta to theta. As for our lower and upper limits on our integrand, well, when x equals 2, we have 2 equals 4 sine theta, meaning that sine theta is 2 over 4, or 1/2. This gives us a theta value of pi on 6. And when x equals 0, well, hopefully you can see that theta will just be 0. So let's put them in there. Now dx, remember, we are replacing with 4 cos theta to theta. The 2 and the 4 combine to give us an 8. And what do we get on our denominator? Because we have 16 minus x squared, but x is 4 sine theta, we need to square 4 sine theta, which is 16 sine squared theta. Notice that we can drag out a common factor of 16 down here, and so when that comes out of the square root, it'll be a 4. 8 divided by 4 is 2. So let's put that 2 out front, of the integral. And what are we left with? We still have cos theta to theta here. And now, underneath the square root sign, we just have 1 minus sine squared theta. But 1 minus sine squared, we should recognize that that is simply cos squared. And the square root of cos squared is cos. But cos divided by cos, that's just 1. And so our integral simplifies nicely to being the integral of 1. Because our variable is theta, this means that we have theta. And evaluating at pi on 6 and 0, we get 2 lots of pi on 6. Just as before, this is pi on 3. And so we get the same solution as method 1. Okay, that finally finishes our video. Good luck with the exercise questions.